There. All right. All right. So actually, Mike Bennett doesn't know who you are. Introduce yourselves and tell us about your project.
So we can get the slide going. It has about us on there.
Yeah. We'd probably start our presentation. It has a little bit about each of us on there.
Okay. Sure.
All right.
Go. I let you share your screen.
Okay. All right. So, Chris, Eric, I'm Cooper. So we're all from the Billings Career Center, and our teacher is Mr. Eric Anderson. And we are also a part of a program called Go Baby Go. So we all work together pretty well.
Yeah, we design cars for disabled kids so that they can have a better quality of life wherever they come from, which is just a sum up answer of what we do in other classes and our teamwork. So that's about us.
Yeah, that's awesome program. Go baby, go.
Totally. So our initial brainstorming, it kind of started with having sensors or like a rangefinder type to sense different objects or any inconsistencies in the ground and have the legs automatically adjust to it. But we realized with the time constraints that we had, we probably wouldn't be able to put that all together just on the spot. So that kind of got scrapped. And then some other individual ideas were like just flexible legs similar to like a GoPro stand where you just set it up, adjust the direction and style of how the legs would look to make sure that the object stays upright. Or the other design is to have like collapsible tubes that would wrap around any inconsistencies in the ground, and it would just basically morph over that rock or whatever it was. But that would have to go on the bottom of the rocket where our payload would be dropped. So that idea was also kind of scrapped.
And just a little bit of inspiration for this, we looked at SpaceX for the Falcon 9, and like those were pretty cool landings, like especially since they had kind of a locking mechanism as they landed. And just a lot that we took from that was how low to the ground it was. That would be really helpful for dropping the payload when we were doing that. And just for us to use that, it was a pretty basic, like kind of design for that to use. And it was easily replicated with all the structures that we had to use. So the only other thing we looked at was how to use bugs and kind of biomimic just to see like how we could get flexible structures to have a lot of force and to take lots of impact.
So we took inspiration from a class that we did a year ago called Capstone. And in this class, we made this kind of claw shape, and we liked it a lot because it flexes into the ground while also keeping a strong structure to itself. So yeah, we kind of used it in our project so that it can morph into the train, stealing the idea of what Cooper had on his initial brainstorming, where it can morph into the ground, but it also wouldn't get in the way of the payload when we would drop it. We also realized that this wouldn't be like very practical for the moon because it's flexible right here, but it's really cold on the moon. So we kind of still went with it because we researched, and flexible carbon fiber filaments would still work.
So we used cat's tongue to kind of use as like a grip on like smooth surfaces to get traction, and then a latch almost with how we designed the leg connecting to the arms. As it folds out, the top arm kind of locks itself into place, keeping a strong base for the rocket, and then just the friction for all of the pivot points on the legs, keeping it upright and being able to close onto the bottom as the rocket takes off.
So that's just what we.
So those are our cans that Glenn recommended we use to get an approximate weight to keep that going. So these are all of our working drawings.
This one's on the top because it has a single connection for the bar. And then our next few, some of them just have a single ring to connect so that we have 2 bars on the outside of those. And that was really just to keep it more solid on that bottom when you're trying to move it out and balance it like that. So there's a single. And the next one.
Those are just the arms that we used. We did some Pythagoras theorem and triangulation to get to right shape so that the foot or the flex feet at the bottom could hold the payload at the bottom while also maintaining its shape and the hold that we want.
Mhm.
Those are just pins that we use to connect the arms, the collars, and the feet. Then the next part was connecting the flexible TPU to everything. And this is just a basic image of how it would balance on a slope, and even with the foot kind of folded in on itself, it still can have quite a bit of support.
Yeah, we really like this image because on each leg you can see that it holds itself all the way out, and then the leg on the far right kind of halfway in, and then the one in the way back is fully folded in. We like how we incorporated that.
So it really just helped you to adapt to the terrain when you can use it in like any bend like that, just to keep it balanced.
So this is the first design. This is
Wow.
way past. Pardon?
That's awesome. Keep going. I really like your shock absorbers, and I know that in the PowerPoint it said it didn't matter if your rocket was straight up when it landed, or it could be on an angle too, just like that other picture that you just showed. Your rocket was on an angle, but it didn't fall over. That's good. That's a go. So, I'm sorry to interrupt you.
No, you're okay.
Okay.
So before we got to this point, this was our first actual prototype to where we were trying to get the legs to, or we'll just call it the feet at the bottom to hold the payload as extra support. We do have another method. We're probably just going to use lashes to keep the payload intact, but as like an extra measured feature, we're going to have the feet attached at the bottom. So this was our first design. It wasn't very practical and controllable, so we decided to add another arm set to it.
Oh.
And just with the final design, you can see on the left and the right pictures for those, they can kind of fold like that. So like we talked about landing with it in that closed position. So as much as the like weight would go into that, you could kind of form it into the ground just in that shape with the flexible material that we had. So we didn't know if that would help with any of the landings, but where it could, it might be used like that. And otherwise, like we had to hold the rover instead of the cans. So we thought about just making a little dish that's about exactly the same size as the can. And then you can use that to hold it just about the same way you would for the cans. So there's just a little bit of the math for the triangulation that we use to keep all the triangles at the right height. And then all the way on that right is that final design.
Wow.
So the design that we have right now, after we removed the cans just to kind of see the shape that we had, we realized that there's a lot more mobility with the bottom ring. So we were thinking about maybe doing an inside ring surrounded by ball bearings that allow for more free movement with the legs.
And just doing that would allow you to kind of control each one independently by the way that they're rotated against each other. So like we thought it'd be really cool, since what we did mostly right now was a model, to just add in some kind of motor capability so that you can move it like that, you can move it around the rocket, and you could adjust like how far it's bending when it lands.
One thing, guys, just thinking out loud here, research how the solar panels rotate on the space station and see what type of bearings they use.
Okay. Will do. Thank you.
Sure.
I'm going to stop share so you're back on video if you guys want to show your actual.
Oh,
Cool. So our current design is in front of Chris here.
Nice.
These were some of our original designs that we had.
can you bring it up closer to the camera, please?
You guys want to do this camera or that one? That one?
We'll just do this one.
Yeah, we'll just show how it
Yeah.
moves.
So we have this one. These cams kind of detached in this morning. So we have this. This. Actually, let's just go to the other one. It's bad resolution.
We'll go short camera. You can see it better.
Perfect.
Is that just stable?
Yep.
So we have this.
Yes,
block,
perfect.
and it will open up.
Okay.
The things. I'll have you do this.
Kind of like an umbrella.
Yeah.
Yeah.
And I'll just take it off really quick so you can see how we control it independently. Too good at attaching them. Okay. So basically, you have it like that, and right here it's going to be sitting down. So as they move closer together, it kind of grips a little bit more. All the way at the top, you can kind of have it to go down like this. You can move them leaning away, and they adjust the ones across from each other. And that really just helps you to kind of lean it as you go.
Oh, really?
Here, we'll put it on the side.
You can. This one.
Yeah.
So you can kind of have
It's
it
like-
bend like that. You can have it stretched just a little bit more.
Mhm.
But basically, we're just trying to keep a balance between the heights that these are adjusted to and how far down that payload goes.
So that. Here, let me show these original ones.
Nice.
It's got some original connections.
So the original connections that we had, we originally put them in half and we were going to glue them together. But we realized that the glue was like getting in the way and preventing us from being able to move that color. And then these were just the original arms that we would use. They connected kind of right in the middle and would hold in place with the collar. But we then moved to just like a singular point, just having two arms and that pin that holds everything in place. It was a lot simpler than trying to figure out the different arms and flexibility of having two arms connected onto one singular point at the same time.
Wow. Well, I'm impressed. That's really kind of very cool. I love your engineering design. That is awesome. Mike, do you have any comments? Anything you think that they can improve on?
Well, can we open up the CAD drawings? I saw that y'all were using Autodesk Inventor. That is cool.
Yep.
And just a couple of hints, just from what I see, just from my point. So if we could open those up, I'll give you a couple of hints.
I think do you want me to go send them to you real quick?
They're on the slide.
Yeah.
Are you talking just the working drawings that are
Yes,
on
sir.
the slide? Okay.
On the slide will be fine too.
Okay.
And guys, I heard y'all talking about using. So basically, y'all were thinking at first about doing a LiDAR type detection.
Yeah.
Nice. I love your engineering notebook.
Yeah, isn't that cool? They all have that. There.
Okay. A couple things that, just from my point of view, that I had to learn too when I came on the side is that in the aerospace industry, we use almost no hidden lines at all. So if you have a hidden line, do a section instead. And the section lets you see the internal details. Also, if you have a hole, put your center marks in, and that way you can dimension to those. And I'd say probably go ahead and do an angular dimension. And I'm sure these are 3 features equal distance apart, but I'd probably call that out. And I know this is PDR, so this part, what you've got right now, still looks great, guys. So just a couple of hints that we do.
I have one more question because I hadn't looked at these working drawings before this, and I was thinking the same thing with the center points and stuff. But when they're dimensioning, shouldn't they be using like a dimensioning technique where they're coming off of the common corner, like on that front view where they're coming off of the left side? And then like they instead of that, they'd have that 0.41, and then they'd have like 1.42 to the next one, and they'd be coming off of that common corner right there.
They could, or they could also do the dimensioning style that uses the center and lets you choose the areas around it. It puts a dimension line, looks like a hidden line, dimension line around it, and you could call that radius or that diameter out, perhaps.
Okay.
There's another way. Ordinate dimensioning we use a lot for our flat type of drawings, like sheet metal and things like that. And I think that may be the one you're talking about is ordinate. On this, since it's circular, I'd put the center mark in, and then I'd do the around it, see if you could do it like a diameter around it, and then how far it comes out and things like that. But it looks good. I like impressive on the design, guys. For years I taught AutoCAD and Autodesk Inventor, so I saw this and jumped at it. What about your other slide?
Pardon?
These are the two slides right here.
No, there's
There's a
more.
couple more, so we have.
Okay. And I'll be quick because I know this is PDR. For example, when always put the center marks in and dimension from the center marks and what is the overall length. I know you can add the radius of this in on each end, but if you give it to, say this was going to be manufactured, if you give that to the machinist, that helps them. That way they don't have to do calculations also.
Yeah.
If you know a simple part, but looks good, guys, and well thought out. Well thought out.
Awesome. Great presentation and great work. And thank you so much, Mike. And we have another Montana school. It's
Great.
in Bozeman, Montana, Gallatin High School, and they're up now.
Thank you guys.
So, but thank you all so much. I'll come and visit you soon. Okay, bye-bye.
Bye.
You can stay on. Gallatin, your next door neighbor is on now. It's their next door neighbor. It's 125 miles down the road.
Wow.
Next door neighbor, Montana. Yep.
Yeah. Good
Anyway.
morning.
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 How is everyone doing? Do you have snow?
Not yet.
Not
Just
yet.
frost.
Oh, okay. So we got Mike Bennett on, and is it all right if I record you?
Yep, that's
Yes.
fine.
Okay. And Mike is helping review today, and he's been in Hunch longer than me, and not too many people can say that.
Anyway, I'll share our screen here.
Was it 20 years this year, Flo? I think I've been there.
Yeah, because Hunch is only 21.
Yep. Yeah. So I guess is there anything else you need from us before we start? Can we just jump into it now? So
Jump right in because we're a little late already.
perfect. Yeah. So we have the lunar landings and payload delivery. Obviously, it's just kind of the slide that we just put together. You guys are familiar with kind of the constraints and the problem. Basically, just need to land a rocket on the moon.
So can you put it in presenter mode? It is not quite in presenter mode,
Ah, crap.
so that we could see it better.
Mm-hmm.
Is that
There we
better?
go.
And also, Dave Schlithing in Colorado just joined us. Good
Hey,
morning, Dave.
Morning. How is everybody?
Good. We're in Gallatin High School in Bozeman, Montana. Dave's from
Good.
Colorado, so he knows Montana too.
All right. How's this look for you guys?
Perfect. Thank you.
Great. So we kind of looked at similar solutions. Remy was kind of looking into the shocks and struts, kind of working on the payload side. So I kind of let him talk about what he's kind of seen with the similar solutions and the different legs.
Yeah, so I originally thought about looking to rally cars and trophy trucks because they have ginormous suspension with a lot of travel, which could transfer very well into lunar legs and allowing them to land smoothly and not tipping over. I kind of got a lot of inspiration from like the 4-bar linkage that you can kind of see in the picture of that chassis there. It has great, excellent travel and dampening properties. Then we also look towards some of the previous legs and kind of how they work and how their feet kind of sit on the ground and up above what's it called, the lunar, that lunar dust.
A regolith.
Yeah, the regolith.
Let's see here. Yeah, and then with Payload, we kind of worked on this, Dakota and I. We kind of looked at what they've been doing, like with the SpaceX rockets and kind of how those work with the cable system. And then we went off with the slides that we had for kind of the project description or whatever. We kind of looked into the sky cranes for the helicopters. So we've kind of looked into different things like that with a 5-point connection. Also looked into like a Chinese finger sort of for grabbing the can. We haven't been able to do too much testing on that quite yet, so we're kind of still figuring out how well that's going to work. That was kind of something we thought about. Yeah, they're also called marine cables. So the materials, this is more for our model. We're still working on kind of the materials we want to use for the main rocket, but just 3D printing, resin printing, and there's these cool sets. They're called erector sets, basically. A lot of robotics teams will use them. I think we've had a couple teams here that have used them. So that'll make it easy for the different legs, so we can kind of modify it easier than printing it out and then reprinting. And then our later models will use the laser cutter and cut out some actual metal. It's going to be a little bit more customized to what we need. And then we looked at the Pika shielding. We looked into that further and figured out that's not going to work. And then that's just descriptions of what they had for the other rockets or other landers they've had on the moon. Yeah, so for our brainstorm, like I said, just looking at the Chinese fingers, which would cause it like friction grip, basically, with some sort of attachment on the bottom to kind of keep it from slipping. And that would just kind of have nice, even pressure around the can that would allow it to not slip and just be more secure during payload. And more moving parts, obviously, so we're kind of still figuring that out. Yeah, so basically what I just said in that slide. Yep, and that's kind of what we looked at so far. That was something the other teams had in previous years. So in the right picture there, just haven't said tape, obviously, it'd be some sort of hooks. So that would allow it to grab the bottom of the can, but then it would tighten around the rest of the can evenly. So there's a few things we still have to look into that, obviously. And then, yeah, brainstormed. I think this is kind of more up his alley, so.
Yeah, I was thinking about using some sort of shock absorber as seen on like the trophy truck. And then just using some RC car suspension to make that. And then probably using 4 legs. We were thinking about 3 legs, but it would be too easy to tip over on that surface. So I think we're going to end up going with 4. Next one.
Yeah.
And then I actually ended up calculating the force on the lunar lander legs. I found it to be about 0.3 newtons of force on each of the legs from the 200 mil drop.
That's Earth gravity, right?
Yep, on Earth gravity, not the actual thing, what we're experiencing. And then do we have any questions? Yeah. Which I think we already went over, right?
Yeah, I think we went over these when we saw you in person here, Flo, but we can ask the rest of the people.
Sure.
It was talking about transporting the rover. And it seemed like when we scaled the rover up, it was, I think, 64 feet tall or something like that, which didn't seem right to us. So we're trying to figure out how we're supposed to transport it. We can put it in some sort of container, like the can. It fits in the Rotel tomato cans perfectly, actually. So can we put it in the can to kind of make it easier to transport and deliver? And yeah, so how we're kind of supposed to deliver it, or if it's supposed to just be in the open and have some sort of modification to the rover to attach to the rocket.
So do you understand their question, which is a good question, because I actually asked Glenn something similar to this. Can we put the rover in the bottom can? Because you have 2 projects. You have one, deliver the rover, and the other is to deliver the crew or supplies in the bottom can. Can we just put the rover in the bottom can, or can we put it at the bottom, outside the bottom can?
So I got a couple of comments and a question for you on that.
Yeah.
Okay.
So first of all, guys, have you got the cans of diced tomatoes and beans that you need to build your rocket fuselage?
Yeah. So we've
Can you see them right now, or are they still on screen
yeah.
share?
So we have
Yeah,
all
you
these.
can stop
Yeah, why don't you
sharing your
stop sharing
screen.
for a minute
Yeah.
and let's take a
There you
look at
go.
what you got there.
There you go. Yeah.
All right. Yeah. So we've
Now you
kind of
can-
got. We haven't designed it quite or like attached it, but we do have our
Okay.
cans. We did print the stuff out. We do have the rover, which does
Uh-huh.
fit perfectly inside the can. So we didn't know
Right.
we pretty much put it inside another can and then have that for delivery. And then we'd only have to worry about the payload or like one type of delivery system since that
Okay.
rover fits in that can.
So here's a couple of thoughts. First of all, I'm glad that you guys have got your materials together. And one of the things that I would encourage you to do as soon as you can is to just kind of tape this thing up. You don't need to worry about securing it firmly at this point, but you need to be thinking about, just dropping this, right? To get a perspective on what kind of impact you're going to have. Believe it or not, there's a fair amount of mass just in those cans that you have, especially when your payload is that one can of baked beans on the bottom. And that's, when you start doing that, I like the fact that you said you're going from 3 legs to 4 legs for stability purposes, etc. The one problem that you have is that if you put that rover in the can as you have, the orientation is going to be wrong, right? In other words, there's not going to be a mechanism that's going to be able to allow this thing to kind of swivel from a vertical to a horizontal position before this thing is lowered to the ground. So
Yeah.
I would encourage you to come up with a delivery system for your payload that allows you to just use that rover without the can on it,
So
right?
just deliver the thing in kind of in the open air.
Exactly. And there are a number of factors here that we're kind of ignoring in terms of the initial phases of all of this, right?
Yep.
So you should keep it specifically to those specifications. You want to do one test with the baked beans, one test with just the rover. The real issue here is your drop test. How effective are your legs at absorbing that amount of force as it's being dropped so that the whole thing doesn't fall over? And the second is the mechanism that you're designing to release or to drop that payload onto the surface, right? And when
Yep.
you think about it, there's two challenges here. One is legs, and one is a delivery system.
Yep.
And chances are, when it gets to the level of a CDR, we're going to see some very impressive legs, and we're also going to see some very impressive delivery systems, right? Mechanisms that will lower this. And selecting the finalists may involve picking some teams that came up with really good legs and some teams that came up with a very good delivery system. Because when you think about it, we kind of hybridize a lot of stuff. We pick one good idea from one project and combine it with another idea from a separate project. So as you're working forward on this, you may find that your design ideas, et cetera, are more applicable to one or the other. And there's nothing wrong with putting a lot of effort into one of those, right? To do both is a big, big challenge,
Yep.
right? So those are my initial things. Back to your original question, don't worry about the bottom can, right? When
Yeah.
you're doing that rover, it should be, just attached to the bottom of the cans and dropped. Now,
Okay.
as to your question about the scaling, I'm not quite sure on that. It would be necessary to look at the calculations, et cetera, because you shouldn't have a rover that would scale up to 64 feet tall.
Yeah, so we kind of scaled up the size of the rocket. I think you
28
kind of
feet tall,
yeah, it's 28 feet tall and
64 feet long.
yeah,
Yeah,
64.
yeah. So I suspect that there's probably it would be a good idea to go back and look at the math.
Yep. So
And you have a former math teacher as a mentor, so she can help you out on that one, right?
yep, I think the way that Dakota had done the scaling is she had matched it with used the same scaling for the rocket,
Uh-huh.
and based on the size of the rocket, scaled it up to the size of what a typical
Yeah.
rocket is.
Yeah,
Yeah,
yeah.
exactly.
Applied the same to the rover, and that's kind of why it was a little goofy.
Okay. But regardless of that, don't concern yourself with the scaling issue right now. It looks like you printed it out
Mhm.
to the appropriate dimensions, et cetera. So go with what you've got.
Okay.
Okay.
All right.
Mhm.
Yeah, and I guess
All
if you go out there, we've also I'll share the screen, reshare here.
Thank you, Dave. That was great advice.
Yeah. So
Click on assembly
I'll
leg.
let you
in the
kind of
Here's
you're kind of want to get this. So
Mike's favorite thing, drawings.
Well, actually, I got a full model for you guys, not just drawings.
Oh my goodness.
I've been working on this leg design here. It has that sort of same four linkage design as a trophy truck, and it comes all the way up and has, I believe, about
Wow.
miles of travel. And,
Quite impressive, guys. You've done a lot.
and it'll just attach to the Rotel can. Yeah,
yep.
with just screws and just bolts right in there. For early tests, we'll probably use hot glue just to figure out like the best placement for it. But
Mhm.
RC car shock right here. These are going to be erector set hinges, and then the rest of it should be 3D printed.
Yeah. I'll be real candid with you. Part of the challenge on this is going to be attaching these legs to that fuselage. Because again, when you start dropping this, you're going to realize there's a lot of force there. My concern is, and you may be able to do this just kind of as preliminary testing, but I don't think hot glue is going to hold up very well. There's a lot of mass there.
Yep, that makes sense. What else have we done? We also built our testing rig. We poured concrete yesterday, so that's sitting in curing
Cool.
in the storage room. So that'll be up and probably ready to test by next week. We have the mortar mix. I think that's pretty much all we've gotten so far.
Oh, and then we also do have a full model of the rocket, but some of it kind of broke for some reason, just because of on shape. But this is
Now, does on shape allow y'all to do a stress analysis of the different parts?
I don't believe.
I don't know on shape. I'm sorry, I don't know this.
I don't know if it does. I don't know it well enough to know. We can take
Okay.
Does Fusion?
Fusion does.
So
Yes.
it might be possible because I have a Fusion account to
Yeah, I can get you Fusion.
bring that into Fusion and then do that.
Fusion also has a design simplification tab too. So you can put your design in and it'll go through and analyze it.
That might be useful.
Very nice. One thing on those sliding, like Dave was saying, hot glue is probably not going to hold this. But if you put some type of tab or a bump out or something above where those legs go, so if they do try to shift, they're going to hit that bump, and that'll help hold it, not just glue. So
And
you've
that
got
kind
two things holding.
That segues kind of into a question that I would have for later year, because like well past kind of getting close to that CDR, is if we can actually 3D print the fuselage of the rocket, just because then we'll have more, we can kind of change the outside and actually add better attachments for the legs, and that'll kind of allow us to have more customization for the rocket, so we're not just stuck using cans all for the whole year. Is that something you guys would be willing for teams to do, or do you want us to pretty much use the cans for the whole year?
my sense is it's an okay thing to do, right?
Yeah,
I mean,
mine too.
as long as your weight distribution, the mass of your fuselage matches the mass of the cans combined, right?
Yep.
And you want to make sure that the distribution, where the weight is, et cetera, matches the other. I don't see a problem with that.
Okay.
Yeah, I don't either. But Dave's comments, yeah, try to match up because we want it standardized, kind of.
Yeah, we've got to be comparing apples to apples. So
Right.
if any teams decide to do this, they're going to have to be very close on their tolerances, et cetera, to make sure that you're doing the same thing as with the cans themselves.
Yeah, the documentation that you provide will have to show that it is apples to apples, like David said.
Yep. Another thing I kind of thought about is if we find a good system for landing, even scaling it up so it's a bigger and heavier rocket, just for proof of concept, and then maybe dropping out from a higher height on a steeper slope. If we can figure out that good system, I think that would probably also help just with, obviously proof of concept, but that's a ways down the road.
Yeah, just with your testing, but in the end, we want to see this rocket working.
Yep.
Take videos, pictures. Good. All right. Did you have did you have something else to show us? Anything else?
I don't think we have anything else. I was just going to talk with these guys on here, kind of get their thoughts about the Chinese finger that we've thought about.
Okay.
We've got a couple different things. We've got a bigger piece that we got from some team last year. Then obviously there's just little toys that you can play with. So we just didn't know what their thoughts were, if they think that's something that's worth pursuing and kind of checking out, if there's going to be some loophole that we haven't thought of, and kind of what their thoughts are.
Good question.
Well, guys, I failed to mention that that's an intriguing idea, right? That's some innovative thinking. Now, it's going to take some work to flesh that out, but again, back to my earlier comment about putting your focus either on the payload delivery system or the legs, you've got something that's pretty unique there, right? I would definitely like to know what Glenn thinks of that. It's unfortunate he can't join today, but I would follow up with an email to Glenn and tell him what you're thinking about, because I think that's go with it. I'm impressed. Creative thinking.
Go ahead, Dave. Sorry.
No, that's it.
I'd say see if there's a commercial application already out there.
Yep.
There maybe. Did y'all find some?
Yep. So I looked into it pretty in depth. There's a lot of companies that use them for marine cables. So they have these big pipes basically, and they attach maybe to 3 feet of the end of that big wire, and then attach it kind of like what we're talking about with our can, and then it can pull out hundreds of feet through that pipe. And I think what I kind of read and why those work well with those marine cables is because it's the easiest mechanism to get through that pipe because it's a small area. So marine cables, there's a few other applications I think I'd written down somewhere. Go back 3 pages.
And one of the reasons I say that is we actually, especially in the flight config, will use, it's called commercial off the shelf. So if there's something that is already existing, you can either use it as a guide for your design, or how could this be modified to work? So at least on ours, sometimes it's not all created brand new. It's taking what's existing and making it work for your application. Kind of like you were talking about the landing gear and the struts and things like that.
Okay.
Yeah, definitely keep looking. That's what we're looking for, those innovative, out of the box ideas.
Yeah.
All right. But do that. Ask Glenn about it.
Yeah.
But copy me. And you can always ask questions. But
we'd always love to get on a call. So if Glenn is ever wanting to talk through that idea with us, we'd love to.
Yeah.
So.
All right. Well, we got to move on because we're actually almost 15 minutes late, but that's great discussions. Thank you, everyone, for that, and especially Dave and Mike for helping. All right, and you can stay on if you want, guys, because we're going to go to New Jersey.
Nice to meet you guys. Nice to meet you.
Thank you. To Passaic County Technical Institute in Wayne, New Jersey now. So thank you.
Can you hear me?
Yes, we do, and we see the team. And in this, the whole class participates. This is a whole class participation.
Right. We were supposed to go to 10:45. So is there someone that's supposed to be before? We're ready, but is there someone that's supposed to be before us?
Wait a minute. No, you're next. You're next.
Okay. Okay, good. Well, then you're ahead of schedule.
That's amazing. Thank you for being ahead of schedule.
I'm Ali, and this is Isaac, and this is Shazib. And Shazib worked on the release system, while me and Isaac worked on the actual legs. Isaac focused more on the folding, like part of the legs, and I worked on the actual legs. So what we decided to do at first was we were thinking of creating some kind of shock absorption system. So we used we have a kind of shock absorber here, right? But we were trying to figure out how to, capture this. So we decided to put it in a syringe so that it can hold and then also have a longer leg. And then once it lands, obviously the spring shrinks, absorbing the shock of landing. Okay. And then for the folding mechanism, where it could pop out, I'm gonna show it with the third can. It's gonna be connected to the third can right here. We're gonna have a spring from here to the can, where we could compress the spring and it could close this. Also, we're gonna have a PVC pipe from here connected to the syringe, where the syringe could fold upwards. So then when you land, you could decompress the spring and then you could rotate a motor that's gonna pop the bottom part out.
Okay, and for the release system, our idea is to basically have little like pins or screws that go into so it's attached here, and they go into the release system, which is also connected here. I'm not sure if you can see that, but it's connected there. And so basically the idea,
I can show you a little bit.
Oh yeah, I remember that now.
Okay.
Yeah, we can see it now. Thanks.
so basically it's the idea of like a fire alarm locking mechanism. So how you like just twist it a little bit and it locks into place. So our idea is the same, where we just twist it a little and it locks into place. The idea isn't like fully finished right now, but we have some like general ideas. This is the part that connects to the last can, the payload.
Yep.
And we made this, we made the pins, like the idea is to have it like replaceable, like you could attach it to anything, it'll lock in. So this is we sort of built like a pod for the rover. And so you would just put the rover into the pod and you could seal that up, and the pins are on this too, so you can just connect it up to the rocket.
And then I was gonna ask, you want me to show the picture so they can have a better, I feel like this is a better representation of
I
how
don't
it
know.
works.
I guess we lost Mr. Bennett.
No, everyone's here.
Oh, okay.
All right.
Yeah, I'm still here.
Oh, okay.
All right, so this is it extended right here, and then I'm gonna show you the one when it's folded up. So this is an extended image of it. Basically, you can just see how the string pops out, and then there's a motor in between the PVC pipe and the syringe, because the syringe part is mainly the problem with the incline on the moon. We don't know if it's gonna land
on 6%, 6-degree incline, 10-degree incline. So we have the spring, you know, where we can balance it out. And then this is it folded with the motor holding it up and the spring closed. Oh, as well, I didn't mention, we also added a foot pad in the bottom. We added like a circular foot pad, so when it lands on any incline, it doesn't tip over or anything like that. We don't have to worry about that problem.
So we decided that for the foot, we were gonna have a flat plate at the bottom with a small, like part of a PVC pipe on top connected to it. And then at the bottom of the leg, we would have a ball joint so it can connect into the PVC pipe, which would act as a ball and socket. So whatever angle it lands on, the foot will be flat and stable.
You guys want us to talk about how many legs we're going to add to it, like 4 or 3?
Sure.
Guys, do you mind if I ask a question?
Sure. Go for it.
You're using a syringe that you're intending to put a spring inside of?
Yes, a shock
absorber. Correct?
Yes.
Okay. So have you done some testing on that yet?
We've been working on the idea and the research behind this. So we haven't done any testing of how it's going to work, but we have the basic concept of how it works with the spring.
Okay, so the concern that I have, a lot of teams are working with springs right now. The issue is you get a lot of recoil. In other words, you're going to get bounce out of this. What you need to be thinking about is dampening the effect of those springs, right? It's a good idea, but I think what I would do is even without attaching this to the cans, if you can just put some weight on there and do some drop testing to see how much recoil, how much bounce you get, because the issue is if this thing basically here, let me if you start getting this kind of an effect, right? You're going to have more of a probability that this thing is going to tip over. So it's what I'm getting at there is you want to start testing as soon as you can to see how much of an effect you need to have to dampen the effect on those springs. Okay?
That's a very interesting point. So that your springs could make it hop along, and not only could you use some dampening, but also a spring that is suitable that wouldn't happen. And we use springs all the time for space things, but we need them specially designed to work on the situation. And do you remember I mentioned Vulcan Springs to you? They're the ones, they're a company that makes springs for space. And so you should actually figure out the math maybe and the newtons and then get a specially designed spring.
We did call Vulcan Springs. They did not return our calls, but we will try again.
Oh, send an email. Send an email and copy me.
And I'd even say, think about aircraft, because when commercial aircraft land, they don't bounce. So is there something special in their design, the spring, the strut, whatever? Is there a dampening system, like Dave said, that's already built in? Because they can't afford to hop when they land.
Yeah.
So perhaps maybe look and see if there's a system built in for commercial aircraft.
Yep. Gonna have to research that, but I've dealt with Vulcan Springs before on some of these projects. So that's cool. So do you have any questions for us?
You have any questions?
You got the experts here. We got 2 experts here. That's not me. That's Dave and Mike.
I have a question. Do you think that because one of our ideas is to have like the third payload, like have this part of the release system like extend out and to have a motor on the inside to just spin it slowly down. Yeah, like a screw. It just screws it down. Do you think that a motor would be able to like hold the weight and turn it? How big do you think the motor would be if it's like on an actual rocket?
I'm not sure. And I made this reference to a previous team on the solar arrays on the space station. They use a huge ring gear assembly to rotate those. So, and I'm not sure how big the motor is for that, but it's a sizable ring gear that does rotate those solar arrays. So that might be a place to look. I'm not sure.
Yeah, I'm going to defer to Mike on that one. I'm not really sure how to answer that question. It's a good question. I just don't know the answer.
Okay, so I have another question. So you were talking about how we should start testing with our legs. So when obviously on Earth there's a lot more gravity than there is on the moon. How do you think that would affect the spring? Like, obviously, it's going to be a lot different here than in space. So, do you think, like,
the difference if it compresses?
Yeah.
So if it lands, would it affect it differently on the moon than if we test it on here? Like, what would be the differences other than,
So the moon has 1/6 the gravity, right? So maybe you can figure out test it with 1/6 the weight that you're, so, instead of weighing 60 pounds that we weigh on the Earth, we'd only weigh 1/6 that weight. So that might also dampen the spring up, right? Because you're not as heavy. You're much lighter. You're 1/6 the weight.
Thank you.
So, Mike or Dave, do you have any comment for that?
No, not at all. That's true. There is a 1/6 gravity.
Yeah.
And I know that's one thing. Years ago, there was a, and Flo, you can remind me on this. It was actually like designing a bed for the astronauts on the moon, I think.
Yeah.
And that was one of the things they took into account, that they weighed 1/6 of the true weight on the Earth.
That was a project, right? You lose a lot of weight.
They have anything that they think that we should really focus on about the legs or the releases? We don't have no specific questions about it. We just want to know like any advice that you think that we should for sure work on right now that would affect, the landing.
I think the testing to help choose which pathway to go, to see which elements are a good idea. I think, like Dave said, you've got to test it to make sure your pathway is correct on it in all your parts.
This is a problem with being from New Jersey because we don't even start school till the first week in September, and then by the time we get POs written and things like that, we're kind of a little behind, but we'll get there before February.
Yeah. No, you're in good shape. And so is some of the class working? Because this project is really 3 things, actually. It's the legs, right, which is a real challenge. Then it's the delivery of a can, slow and steady wins the race. And then it's the delivery of the van, which I like that you made a little container for it. And I like that you have the can and the lunar rover both using the same mechanisms to deliver it. I would say, all right, so now you have the mechanism to release those 2 things, but I want it to be released slow and steady. So, and that's the question I actually asked Glenn yesterday. I said, well, the release mechanism for the can or the rover, where can that be? Can it be inside the can or can it be outside the can? And he said either way. So because you're going to need a release mechanism to you have a good release mechanism for the can, but you need the can to go down slow and steady, not to fall over, because the crew might be in that can, right? So that whatever mechanism you design, you can have it, he said, you know, at the bottom of the can, or it could actually be inside the can. Does that make sense? Am I explaining that well?
Yeah. That was our idea with the syringes, because once the syringe like slowly compresses, it lowers the whole rocket as well as the payload until it is either really close to the ground or is touching the ground, and then obviously from there it just releases.
Right.
Oh, so and so that's actually that's really cool, I think, because then you don't have to worry about a pulley or something. It will be on the ground. I like that. Dave, do you have any comments about that?
Well, two comments, guys. I got distracted for a second. First of all, relative to your question about, you know, the effect on the moon, Flo pointed out, right, where the moon is 1/6 the gravity of the Earth, but the bottom line is you're building and testing this here, and so is everyone else. So it's fine to do the calculations to determine the difference in the impact force, but you're building this and testing it here. So that's really where your focus needs to be. The other thing is, you know, when you're designing this, keep in mind that you want to have those legs configured so that the space beneath the payload is as minimal as possible after this thing is hit, right? So that you don't have to drop that very much at all, right?
Mm-hmm. That's what they're saying they're going to do.
Yeah, exactly.
Yeah, that's good.
You're on the right course there.
Yeah, and Dave is right again that while it is 1/6 on the moon, your testing is here on Earth, so we can't have it bouncing around from your testing here. Does that make sense?
So basically, our testing should just be working as if it works on Earth.
Right.
Correct.
It will
We're
work.
not really worrying about no gravity. We're just worrying about the fact that how does this land on the moon?
Right.
On Earth. I'm sorry, on Earth.
Right.
Okay.
But we did say, hey, you have to test it on a 6-degree angle slope, you know.
Correct. With the slope, right.
Yeah. But
okay.
But we can't simulate the no gravity or the 1/6 the gravity. So so yeah, test it on Earth. That will be great. That will be great.
Thank you.
All right.
We're good.
You're good. Well, thank you so much. And you can always ask questions. Keep looking at the website, because Glenn has been updating the website. The last time was the 22nd, so maybe a week ago he updated these projects. So I need you to keep checking back on that. But you can ask questions anytime. Just send me your send me your question, but copy your teacher. And you all have a great. How's the weather in New Jersey?
It's cold. It's getting colder.
75 degrees right now.
Oh my goodness. That's still warm. I had beautiful weather the whole week when I was there.
I know.
That was awesome. Okay, team. You have a good afternoon. Thank you. Thank you, everyone in the class. Everyone in the class, wave to us.
Thank you.
A whole class working on this. Yep. Thank you.
Bye-bye.
Bye-bye. And you can stay on if you want, because Glenelg is next. And Glenelg, we are actually ready for you if you're ready for us.
And Flo, I'm going to apologize. I'm going to have to drop off.
Okay, well, thank you. You saved me.
Not a problem.
So
great
much.
project.
I'm so glad. Your input was great. Dave, can you stay with us?
Yeah, they're right. Yeah, I'm good. I'm here.
Oh, thank you so much. All right. So, I don't know, Mr. Gershner, are you ready, or we actually are early? They're not scheduled.
Mr. Gershner is in the other room. He won't be joining us right now, but we are ready when you guys are ready.
Oh, we're ready.
Okay. If you can just give us 1 second, we're going to get the presentation pulled up.
Yeah. And after them, we have a break. Because I try to do these during the time the kids have class. Good morning. It's still morning in Maryland.
Still morning. Morning.
Good morning. Let's see. Andrew and Jacob.
It is now just Andrew and Chabanu. Jacob left the group.
Oh, no.
So it is now just us two.
Okay. And how do you say Nacha Banu?
Chabanu.
Chabanu.
Yeah, just the
awesome. Yeah, forget the end. Chabanu. Awesome. Thank you.
Okay. Can you see our presentation?
Yes. Perfect.
Okay. So we are the Lunar Landing Legs and Payload System from Glenelg High School, Maryland. I'm Andrew Hammond.
I'm Chabanu Atencho.
Sorry.
Okay, so for our problem statement, so NASA needs a reusable landing legs and payload system for the Artemis lunar lander to deliver supplies from a lunar base and to minimize the labor that astronauts have to perform while moving these supplies. A study in 2023 showed that these suits can cause injuries from burns to intense sweating from all the heat, from all the work that they do. They can also wear out their gloves and stuff. And so we just want to make sure that they have to do as little work as possible while we're moving this payload, as well as create a landing system that will accommodate this new payload system.
So some issues to consider as we were designing and thinking of different resources, materials, things that we could try to use were the landing gear has to withstand very significant forces. So on the lunar lander, the Apollo 11, the impact forces were measured of up to 3,000 pounds. Another thing is the lunar surface presents uneven terrain, rocks, craters, etc. And landing on 6-degree slopes can actually destabilize landers. So this was an issue with the Odysseus or the IM-1. And 30% of landing sites could have hazardous features. This comes from NASA's research on the different landing sites that they have chosen for us. And another big thing is lunar dust has been found to damage seals and joints. For example, on the Apollo 11, it was found that the effects of the dust blasting up into the legs off of the propulsion system was almost like a sandblaster. So we have to think about that when we build our designs, that it can actually withstand all these forces of things smashing against the legs. And we also have to think about the fact that space itself is very close to absolute zero. So there are temperatures around the legs of up to 250 degrees Fahrenheit and negative 250 degrees Fahrenheit.
And so some of the things we considered when trying to make our own legs was the Falcon 9 rocket. And so what it had was it had piston sisters. And so it had its 4 legs upright. And so the pistons would then push out and the legs would just fall over and latch into place. So this is a very simple system, and we thought this could be nice to integrate into our rocket if we could. Something that we did find a problem was is that we felt that since they bent inwards into the bottom of the rocket a bit, we felt that could interfere with our payload system. And then we also wanted to make sure that the legs also weren't also didn't with the upper half of our payload system, it did with the ropes and the steel wires that we'll explain later on, which is our integrated system that doesn't interfere as with all the rocking and shaking that might cross over.
So another design that we looked at when we were thinking about our design to put up was the Cargo Dragon, and some things about it. It's actually relatively small for a space shuttle. It's 14 feet by 12 feet in area. It uses a docking mechanism, so this is actually meant for the ISS. This is how they transport a lot of materials. So the nose of the rocket actually opens up, and it will connect to the ISS, and then they will deliver cargoes through the nose of the shuttle. Some bad things about this is that it's very, very heavy. It's actually 6,000 kilograms, the entire thing. But a good side of this is that it's reusable because they've landed it multiple times. SpaceX reuses their rockets. And the way that it lands is it uses a parachute instead of the lands because the legs are obviously detached.
Final thing that we consider is the Odysseus. So the Odysseus, or the IM-1, was Intuitive Manufacturing's lunar landing system. And so the thing that we liked about it was that it had a very simple design. It had 6 legs that had 3 rods each attached to one landing pad. But the problem with it was that after it landed, one of the IM-1's legs broke. So the IM-1 tipped over about 30 degrees. And so we just thought that its simplicity was nice to integrate, that if we could just change the materials a bit, it might give us a good set of landing legs to work with.
So this is our solution matrix, and this is basically what our solutions that we designed, which we will get into some of the pictures of them later. But we rated them, and then out of 10, 10 being the best, 1 being the worst, and then we weighted them to see which ones are actually better, because the rating doesn't necessarily mean that one is better. It just shows higher numbers versus lower numbers. And we found that the arm bolt had the highest rating and the highest weighted score. The steel wire barrel latch came next with the highest rating, the highest weighted score, and then the barrel rod came next with the highest rating, highest weighted score.
So other things we considered was other rockets that were made in the past. So like we mentioned before, the Odysseus, the Falcon 9, the Cargo Dragon. But we also looked at things like the Chandrayaan and the Chang'e 6, as well as the Slim rocket from JAXA. And so what we did was we rated them based on their legs and their cargo systems. And if they didn't have them, we just input estimated values. And so what we thought was the best overall leg design, the best cargo design, as well as what we thought was the best rocket overall. We listed out on the right side, the Falcon 9, we thought it had the best leg design. We thought the Omotenashi had the best cargo design. And so after rating these, we then start to look at what we might incorporate into our system.
So how are we going to design and model this? So the design in NASA HUNCH's website says that it needs to be lightweight. It must be as lightweight as possible, because when it's lightweight, it decreases the cost to launch something. It's very expensive to launch a lot of weight into space. The more weight, the more expensive the launch is. It must withstand a 200 millimeter drop, and the cargo has to be securely attached to the bottom of the rocket. It has to be easily removed by astronauts. NASA doesn't exactly say how many astronauts it needs to be removed by, but we are going to assume that 2 astronauts alone should be able to remove our cargo easily. So how are we going to construct this? 2 Rotel diced tomato cans will be placed on top of 2 Bush's baked bean cans, and then we will pour 2 Quikrete concrete bags into a baking pan, set it, and that will be used as our elevation to drop our lunar lander onto.
So for our latching mechanism, we had a barrel latch and steel wire system. And so what we have is a barrel latch on the bottom of the mechanism. And so then we have steel wires attached to it. So this will allow us to raise and lower the cargo, the payload. And then when it's lowered onto the truck or the system they have on the moon to transport it, they can easily just pry it open, because as barrel latches, they can be difficult to close, but they are really easy that once you just pop them open a bit, it will just fly out open and you'll be able to easily take it off. So we thought this is a very easy system that would be, although difficult to attach on Earth where we have the resources to do so, it'll be easier to remove on space where you might not have the resources to use the force necessary to close it.
So this is one of our designs for a possible foot pad design. And when I say foot pad, I mean the very bottom of the leg will actually touch down on the surface of the moon. And what we were thinking of doing is having support trusses going into a central hydraulic beam that will connect to the actual rocket, and then have piston actuators that don't let the foot pad move too much in one direction, but also resist the force of the ground, so that the foot doesn't necessarily rotate like this, because if it rotates 90 degrees, that's bad. That can crush the foot, that can make it unstable, and that won't increase our chances of success when we land. These are our sources. Any questions?
Wow. Nice job on your presentation. I love your PowerPoint too, but you added, I saw your PowerPoint just without you guys, and you added a lot to that. So thank you. But we're going to let Dave answer any questions you might have. Or Dave, do you have any questions?
The one question that comes to mind first is, you talked about hydraulics.
Mhm.
Now, have you taken into account the temperatures at which any kind of a fluid is going to have to be viable, right? When you build your model, are you intending to use some kind of fluid for the purpose of dampening this landing?
So that was a speaking mishap on my part. I should have said pneumatics. We are planning to use gas
Okay,
powered pistons,
perfect
not
then.
hydraulics. So that
Yeah.
was a speaking mishap on my part.
No. That's it's a common thing, and so you're gonna use kind of a gas compressor for the
Yes.
dampening effect.
Yes.
Are you going to build this, or do you intend to try and use something that's commercially available?
So we have thought about the pros and cons of buying something commercially available and also building it. One of the cons of necessarily buying something that's commercially available is the sizes that they make these pneumatics at. They don't necessarily make them at the size that we need because we need a
Right.
very small one. And yeah, there's RC cars that have pneumatics and stuff, but most of those are hydraulics. They're not gas actuated pistons. And then we could build this, but do we have like a CNC machine to make a
Yeah.
aluminum piston? That's difficult. So we could reach out to some companies and see if they could machine these for them. But with the time frame we are most likely just going to take the route of buying something that's commercially available and hopefully finding a size that's
That's
big enough.
fine. Yeah. No, I'm just curious as to the approach because I see both of them going. I think where the direction you're going with this is actually quite cool, and I'm also intrigued by your release mechanism for the payload. I think you guys have got some great ideas. Have you built anything yet?
No, not yet.
I have worked on a couple of Lego models of the entire rocket itself, just as a physical representation. We actually have that on our site in our mock-up category,
Mm-hmm.
but we have not found any barrel latches yet that are that size. We're working on getting some soon.
Okay. Do you have your fuselage? Do you have your cans of beans and
Yes, we've
okay.
we've
So
ordered all
you okay, so that's really a good starting spot because again, it doesn't seem like a lot. You know, when you think about a few cans and you're actually emptying a couple of these, you don't think there's much mass, but in fact, there is. So the sooner you can get these things together and start doing just some dropping to get a sense of how much force you're actually applying, it's gonna help you, especially when you start thinking about attaching those legs to this fuselage, right?
Yeah.
It's a piece that is going to be integral in all of this. So get them as soon as you can and start dropping it. That's
Yeah.
my most important suggestion.
Okay, so this is Glenelg Merlin, and they're actually tasked to do a lot of research before they start trying to make a model or 3D print anything. And I actually really like that approach because you are researchers. You come up with things that I don't even know about. I was very interested in the injuries that the astronauts have occurred on their spacesuits and while working. So don't worry about not having 3D printed or made the model yet. But keep doing your research. My message is keep doing your research because that's what makes your projects always so wonderful. That you continually do research and come up with these wonderful ideas. So I appreciate that. And your PowerPoints and stuff is really cool. And I like that you already have a Gmail account. That makes it easy for me to know who is asking the question. So, but ask questions anytime and be sure to copy your teacher. I have a question though about the pneumatics. So you're using a gas. Is that going to be an issue on the, I know it's not an issue on Earth, but will it be an issue on the moon?
So when I was researching the different temperatures that gases can withstand, for instance, hydrogen only turns into a liquid at absolute zero, and the actual resting temperature of space isn't completely absolute zero. It's close to it, but it isn't absolute zero. So what we were thinking of doing is trying to do a hydrogen powered pneumatic system instead of maybe an oxygen pneumatic system.
Yeah.
But we would have to research that a little bit more. We haven't completely come up with how that would work.
Yeah, I think nitrogen would also be, a possibility as well. So you're absolutely right there.
Yeah, good. Yeah, well, the temperature affects everything. And whenever you're doing these projects, another aspect of it is what you can build it out of anything. Your prototype could be out of paper or cardboard, right? But we want you to research also what materials NASA should use, thinking that it is $1.2 million a kilogram to send something up to the moon. That's a huge problem. So any cost in material, I don't even think gold costs that much. I know one team doing the cosmic collector of the dust, they were going to line their malar with gold, right? Because that's insignificant cost compared to the cost of sending something up there. So don't worry about the cost of material that you research for NASA, because everything becomes totally insignificant compared to the transportation cost.
Yeah, we've already started to do research into the density of these objects, and as well as like if they can withstand the temperatures of space. Some things we found some metals, but we also found some custom plastics. Although we're not sure about the plastics anymore because of how much they might cost to make it on such a humongous scale.
I think we talked to you in our preliminary presentation about how we were originally thinking about rubber as the base of the footpad, but rubber becomes brittle at less than negative 100 degrees Fahrenheit, and it's hard to heat that back up when you get to the moon. Like, that would be an issue. So we are definitely researching different materials that we can use. Currently, we're planning on going with a more aluminum-based approach.
Yeah. And hopefully we find aluminum on the moon, and then we could 3D print things for it too. So, okay. Well, thank you so much. I sure appreciate that. And if you do have any questions, you know my email. Just copy your teacher. Okay?
We definitely will. Thank you.
Thank you so much. You have a wonderful day.
Thanks, guys.
And so we are done until Jackson Hole, Wyoming joins us. And that's not until, Dave, you and I are on the same time zone. And so is Jackson Hole, 10:30. So we got about an hour and 10 minutes. And can you join us again, Dave?
I think so.
Awesome, because we have Jackson Hole, and then we have two teams doing this from Olympia High School in Washington, and they're on Pacific time. But all three of them will go Jackson Hole, then Olympia, and then Olympia again.
Okay,
and that's it.
Okay.
All right. Well, I'm going to end this meeting, and I've got it recorded, and so I'll put the recording on our YouTube and send everyone the link. So thank you, everyone, so much, and have a wonderful afternoon. Thank you, Dave. Bye-bye.